In this video, we're going to focus on solving some basic problems associated with the drift speed of an electron in a metal and also the current density. So in this example, we have a silver cylindrical conductor with a radius of 1 centimeter and it has a current of 5 amps flowing through it. So let's draw a picture. Let's say this is the cylindrical conductor, and so this is the radius of the conductor. And now there's a current flowing through it, and it's 5 amps. We're given the density of free electrons in silver. It's 5.8 times 10 to the 28 electrons per cubic meter. Calculate the magnitude of the drift velocity in the conductor. Now, if you want to, feel free to pause the video and try this problem. But let's go ahead and begin. How can we calculate the drift velocity in this conductor? The formula that we need is this equation. It's equal to the current divided by N, which is the density of the free electrons in this material, multiplied by the charge of a single electron times the area. So N in this example is 5.8 times 10 to the 28 electrons per cubic meter. We have the current, which is 5 amps. And what is the charge of a single electron? One electron has a charge of 1.6 times 10 to the negative 19 coulombs. And electrons carry a negative charge. But our goal is to calculate the magnitude of the drift velocity. So we want a positive answer. So we could use a positive Q value in this case. Now the last thing we need is to calculate the cross-sectional area of the cylindrical conductor. And because the cross-section is a circle, the area is going to be pi r squared. Now the radius is 1 centimeter, so we need to divide that by 100 to get that in meters. So that's 0.01 meters. And so the area is about 3.142 times 10 to the negative 4 square meters. Now let's go ahead and plug everything in to the formula. So the current is 5 amps. N is 5.8 times 10 to the 28. Q, we're going to use positive 1.6 times 10 to the negative 19. And then the area, 3.142 times 10 to the negative 4. So if we take 5 and divide it by 5.8 times 10 to the 28, and then take that result divided by 1.6 times 10 to the negative 19, and then divide that result by 3.142 times 10 to the negative 4, you should get this answer. So the drift speed is 1.715 times 10 to the negative 6 meters per second. So as you can see, the electrons are moving very slow in this conductor. Now there's two types of motion that you need to be familiar with. There's the random motion of an electron, which just goes everywhere and it moves at a very high rate in those directions. And there's the drift speed of an electron, which flows opposite to the direction of conventional current. And that drift speed, where you have a large group of electrons flowing in one net direction, is very, very, very low. So keep that in mind. Now let's move on to part B. Calculate the current density in the wire. So what is the formula for current density? Current density is represented by the symbol J, and it's equal to the current divided by the area. So we have a current of 5 amps, and the area we said was 3.142 times 10 to the negative 4 square meters. And so in this example, the current density is about 15,900, this is a rounded answer, amps per square meter. Now let's move on to part C. How long will it take an electron to travel a distance of 1 meter? So let's say if this is a distance of 1 meter, how long will it take an electron to go from position A to position B. Now we imagine that it's going to take a very long time because the drift speed is so low. But you can use this formula. D is equal to Vt. So the time is going to be the distance divided by the drift speed. So that's a distance of 1 meter, and the drift speed is 1.715 times 10 to the negative 6 meters per second. So this will give us the time in seconds. And so this is about 583,000 seconds if you round it. Now approximately how many hours does that represent? So if we divide it by 3,600 seconds per hour, this is approximately, if you round it, 162 hours. Now if we divide that by 24 hours per day, it's roughly about 6.7 days. So it takes an electron a very long time to travel from A to B, to travel a distance of 1 meter in this conductor. 6.7 days is a long time to travel for a distance of only 1 meter. Number 2, a current of 2 amps flows through a metallic conductor with a cross-sectional area of 1 square centimeter, and it has a drift speed of 0.05 millimeters per second. Now, if the area of the conductor reduces to 0.5 square centimeters, what is the current in this section of the conductor, and what is the drift speed? So on the left side of the conductor is going to be relatively large, and then the cross-sectional area will be reduced. So let's call this A1 and A2. So the area on the left is 1 square centimeter. On the right side, it's 0.5 square centimeters. Now we have the drift speed on the left side, and it's 0.05 millimeters per second. So how can we determine the drift speed on this side? Now the current on the left is 2 amps. And what is the current on the right side? Now for a metallic conductor, the current is going to be the same. The amount of current that enters the conductor is equal to the amount of current that leaves the conductor. So this answer is not going to change. So A is still 2 amps. Now part B, what is the drift speed? Now perhaps you went over fluids and Bernoulli's equation and equation of continuity. If you went over that chapter in physics, you know that if you have a fluid like water flowing through such a pipe, if you decrease the area, the speed will increase based on the equation of continuity. So imagine if you have, let's say, a water hose and water is coming out. If you partially block it with your finger, the water is going to be forced out at a higher rate. It's going to come out at a greater speed. So if you decrease the area, the velocity will increase. And in that chapter, perhaps you've seen the equation looks like this. A1V1 is equal to A2V2. Well, we could derive that same equation in this problem. We know that the current is equal to NQ times the drift speed multiplied by the area, if you rearrange the formula that we used in the last problem. So we could say that the current is equal to the number of electrons per cubic meter, that's N, and for a certain metal, that's going to be constant. The charge per an electron is going to be constant. And on the left side, we're going to call the drift speed V1 and the area A1 because that changes. On the right side, we're going to have V2 and A2. Now, N is not going to change, and Q is not going to change for the right side because it's dependent on the material, and Q is just the charge of an electron. So since this is equal to the current flowing through the circuit, and since the current is the same, these two have to equal each other. And we can cancel NQ. And so we get the equation of continuity for circuits. So A1V1 is equal to A2V2. So what does this mean? It means that if we decrease the area of the conductor, the drift speed will increase as long as the current remains constant, which it should. So let's go ahead and calculate the new drift speed. So A1 is 1 centimeter square. We don't have to change it in meters for this equation. because as long as these two have the same units, it's going to be fine. V1 is 0.05 millimeters per second. A2 is 0.5 centimeters squared, and so V2 is going to be in millimeters per second as well, because these units cancel. So it's going to be 1 times 0.05 divided by 0.5. And so the new drift speed is 0.1 millimeters per second. So notice that we decreased the area by a factor of 2. It went from 1 to 0.5. And so the drift speed increased by a factor of 2. It went from 0.05 to 0.10. So the area and the drift speed are inversely related. Now let's calculate the current density in both sections of the conductor. So what is the current density on the left side? We know that the current density is the current divided by the area. So for the left side, it's going to be a current of 2 amps divided by an area of 1 square centimeter. But let's get this answer in meters. So how can we convert 1 square centimeters to square meters? Well, we know that 1 meter is equal to 100 centimeters. However, we need to square it because we have centimeters squared. So it's 1 divided by 100 squared, which is 0.0001 square meters. So 2 divided by this value is 20,000 amps per square meter. You can also describe it as saying it's 2 amps per centimeter squared. So if you write 1 square centimeter here, you could do that, but just make sure to put the appropriate units. But I'm going to put it in the standard units, so it's 20,000 amps per square meter. So notice that the current density is not constant. Even though the current flowing through the circuit is constant in both sections of the conductor, the area is not constant. So to calculate the current density is going to be 2 amps, and if we take 0.5 square centimeters divided by 100 squared, the area is going to be 5 times 10 to the negative 5 square meters. So 2 divided by that result, this will give us a value of 40,000 amps per square meter. So as the area decreases by a factor of 2, the current density increases by a factor of 2. And as a result, the drift speed increases as well. So it turns out that the drift speed and the current density are directly related. So we know that the current is equal to NQ times A times the drift speed. So if we divide both sides by A, this becomes the current density, which is represented by the symbol J, and that's equal to NQ times VD. So as you could see, the current density is directly proportional to the drift speed. If you increase the drift speed, the current density will increase. Number 3, the drift speed of the electrons in a wire is 0.04 millimeters per second when the current is 3 amps. Now, if we increase the current to 9 amps, what will be the new drift speed? So we know that the current is equal to NQV times A. So let's make a ratio between the second current and the first current. So the first current is going to be NQV1 times A. Now, we're dealing with the same wire, so the cross-sectional area doesn't change. And the density of free electrons doesn't change, so we don't need a subscript for N. And Q is going to be the same. So I2 is going to be NQV2 times A. So N and Q are constant in this example, and the area is constant. So notice that the ratio of the two currents is equal to the ratio of the drift speeds. So therefore, if we increase the current from 3 amps to 9 amps, if we increase it by a factor of 3, the drift speed should increase by a factor of 3. So it should be 0.04 times 3, which is 0.12 millimeters per second. But now let's confirm this answer with this formula. So the second current is 9 amps. The first current is 3 amps. The first drift speed is 0.04 millimeters per second. And let's calculate the second drift speed at a current of 9 amps. So we need to cross multiply. This is going to be 3 times V2, and then that's going to equal 9 times 0.04, which is 0.36. Now let's divide both sides by 3. So 0.36 divided by 3 is 0.12. And V2 will have the same units as V1 because on the left side the unit amps cancel and there's nothing else left over. So it's 0.12 millimeters per second. So that's the new drift speed at a different current. Now let's move on to number 4. A charge of 720 coulombs flows through a copper conductor with a radius of 2 centimeters every 4 minutes. The density of copper is 8960 kilograms per cubic meter, and assume copper contains 1 free electron per atom. And we're given the molar mass of copper. It's 63.55 grams per mole. So that's the atomic mass unit of copper. You could look that up in the periodic table if you want to. Calculate the current flowing through the conductor. Now the current is simply the rate at which the charge flows. So it's the change in the quantity of electric charge divided by the change in time. So we have 720 coulombs of charge flowing through the conductor every 4 minutes. Now you need to know that 1 amp is 1 coulomb per second. So we need to get the time in seconds. 1 minute is equal to 60 seconds. So 4 minutes is 4 times 60, which is 240 seconds. So if we take 720 and divide it by 240, that will give us a current of 3 amps. So that's the answer for part A. So I'm going to save this answer because we're going to use it later. Now let's move on to the next part, part B. Determine the number of free electrons per cubic meter in copper. Now how can we do this? The best way is through a conversion process. Our goal is to get the number of electrons on top and the cubic meter on the bottom. Now notice that we're given the density. So starting with the density, we already have the number of cubic meters on the bottom. So we could say that there's 8,960 kilograms of copper in a volume of 1 cubic meter. And so that's the density of copper. Now eventually, we're given the molar mass in grams per mole, so eventually we need to convert kilograms to grams. Now 1 kilogram is equal to 1,000 grams. And so the unit kilograms will cancel. Now we can convert grams to moles. So there's 63.55 grams of copper per 1 mole of copper. Now for those of you out there who are wondering, what exactly is a mole? A mole is simply a quantity. It's a very large quantity of stuff. So for example, when you hear the word dozen, what do you think of? Perhaps you think of a dozen eggs. A dozen eggs is 12, or 12 eggs. If you have a dozen calculators, you have 12 calculators. If you have a dozen pens, you have 12 pens. So a dozen is really a quantity. A mole is a large quantity. It's 6.022 times 10 to the 23. So if you have a mole of pens, you have 6 times 10 to the 23 pens. If you have a mole of books, you have 6 times 10 to the 23 books. So just as a dozen represents 12, a mole simply represents a large quantity of something. So 1 mole of copper atoms is 6 times 10 to the 23 copper atoms. Now, notice that there's 1 free electron per atom. So 1 mole of copper atoms will contain 1 mole of free electrons. So now we can get rid of this unit. Now the last thing we need to do is convert moles of electrons to the number of electrons. And so 1 mole of electrons contains 6.022 times 10 to the 23 electrons. Now notice what we have left over. So we now have the number of electrons per cubic meter. And so that's going to give us N, the density of electrons in this material. Now let's go ahead and get the answer. So it's 8960 times 1000 divided by 63.55 times 6.022 times 10 to the 23. And so it's going to be 8.5 times 10 to the 28 free electrons per cubic meter. So that's the density of free electrons in this material. And so I'm going to rewrite the answer here. Now let's move on to part C. Calculate the drift speed of an electron in copper. So we know that the current is equal to NQ times the drift speed times the area. So the drift speed is going to be the current divided by N times Q times the area. So let's start with the area first. That's going to be pi r squared. The radius is 2 centimeters, which if we divide it by 100, that's 0.02 meters. So 0.02 squared times pi, that's going to be 1.2566 times 10 to the negative 3 square meters. So the drift speed is going to equal N, which is 8.5 times 10 to the 28, multiplied by Q, which is 1.602 times 10 to the negative 19, and then the area, 1.2566 times 10 to the negative 3. And then we have a current of 3 amps on top. So the drift speed in this example is 1.753 times 10 to the negative 7 meters per second. And the reason why the drift speed is so small is because the area of the conductor is relatively large. Let's say if the radius was 1 millimeter, for example, this would be significantly higher. It might be 10 to negative 5 or even 10 to negative 4. So just keep that in mind. So if you have a very high radius, if the radius is very long, then the drift speed is going to be very small. But if you decrease the radius to like a millimeter or half a millimeter, then this will increase from like 10 to negative 7 to like 10 to negative 4 or 10 to negative 5. Number 5. A wire with a diameter of 5 millimeters has a current of 7 amps flowing through it. If the drift speed is 0.04 millimeters per second, what is the density of free electrons in this material? So we know the current is equal to the density of free electrons times the charge times the area times the drift speed. So in this example, we need to calculate N. So that's going to be the current divided by Q times A times the drift speed. So the current is 7 amps. The charge per electron is 1.6 times 10 to the negative 19. The area is pi r squared. And so 5 millimeters, you need to divide that by 1,000 to get it to meters. So that's going to be 0.005 meters squared. And the drift speed is 0.04 millimeters per second. And milli is 10 to the minus 3, so you could say it's 0.04 times 10 to the negative 3 meters per second. And so let's go ahead and plug this in. So this particular material has an electron density of 1.39 times 10 to the 28. So that's the number of free electrons per cubic meter. An atom have a lot of electrons that are not free. Only a small number of electrons are free to move in an atom or in a metal. So just keep that in mind. Now, how can we take this value and calculate the density of the metal? Now, one thing I need to give you is the molar mass of the metal, which I didn't give you that information. So let's assume that the molar mass is 80 grams per mole. Now, this may not be a real element, so I just came up with this number. Just keep that in mind. I just want to show you how you can take this value and convert it back to the density of the metal. So start with this number, 1.39 times 10 to the 28 electrons per cubic meter. And our goal is to convert electrons to kilograms. Now we need to convert electrons to moles. So there's 6 times 10 to the 23 electrons per 1 mole of electrons. And it's going to be 1 mole of electrons per 1 mole of the metal, which I'll write M for the metal. And then the metal has a molar mass of 80. So 1 mole of the metal is equivalent to 80 grams. And then convert grams to kilograms. There's 1,000 grams per 1 kilogram. So it's 1.39 times 10 to the 28 divided by Avogadro's number times 80 divided by 1,000. And so the density for this material is going to be 1846.6 kilograms per cubic meter. Now let's use silver as an example. Silver has a density of free electrons of 5.85 times 10 to the 28 electrons per cubic meter. And there's 1 free electron per silver atom. The chemical symbol for silver is Ag. And the last thing we need is the molar mass of Ag. It's 107.9 grams per mole. So with this information, estimate the density of silver metal. So just like before, we're going to start with the number of free electrons per cubic meter. And then we're going to convert it to moles using Avogadro's number. So the number of electrons cancels. And for every mole of free electrons, there's 1 mole of silver. And now we can convert this to grams using the molar mass. 1 mole of silver has a mass of 107.9 grams. So these units cancel and those units cancel. The last thing we need to do is convert grams to kilograms. There's 1,000 grams per 1 kilogram. And so now we could cancel grams. So we have the units that we want, which is kilograms per cubic meter. So this is going to be 5.85 times 10 to the 28 divided by 6.022 times 10 to the 23 times 107.9 divided by 1,000. And so in this case, if you round it, it's about 10,500 kilograms per cubic meter, which is the same as 10.5 grams per cubic centimeter. So that's how you can calculate the density of silver if you're given the number of free electrons per cubic meter.